Okay, so we just talked about your project parts status right before. A couple of you are going to come see me. We're going to do a little bit of review. Op amps are a hard thing, and so we're going to go back, and I'm going to show you a little bit different way to think about op amps for the first couple slides. And then we're going to finish the operations that we can do. Today we're going to do calculus with op amps at a very high level, as in I'm going to show you the circuit and show you that there's a formula, and we're not going to follow all the circuit analysis. That gets a little hairy if you're not really familiar with it. It's something that's worthwhile doing, but I didn't feel like it was worth spending an entire lecture on. And then we're going to do instrumentation amplifiers at the end, which solve a lot of the problems that op amps have for what we're going to do in the laboratory often. Okay, so you remember we talked about these operational amplifiers. This is the symbol for it. They're generally supplied with a bipolar supply, though sometimes you do single-ended supplies, so ground to 9 volts instead of negative 9 to 9 volts, let's say. And they have two inputs, a non-inverting input and an inverting input, and an output. And we learned that these things, the ideal op amps, have a very high input impedance and a very low output impedance, and an effectively infinite open loop gain, right? So with no feedback, they have a gain of infinity in theory and of a couple 100,000 or a little bit less in practice. And so we did things like comparators, right? Okay. So Chris Gamble runs this course called Contextual Electronics, and he actually explained it this way, which I thought was a different way to look at it instead of having the gain on this variable resistor on the output kind of model that we looked at before. I think the op amp always wants both of its inputs, the inverting and non-inverting, to be the same value. And if they are not the same value, it will go positive or negative depending on which is higher. Okay, that's in an open loop configuration.
Does that mean which has a higher absolute value?
Yeah, so if the non-inverting input is higher, then it will swing positive. If the inverting input is higher, then it will swing negative, right? Okay. So we looked at this circuit, which was a voltage follower. And I think a few people maybe didn't quite follow what exactly was going on in this circuit. So let's look at it again, thinking of it in those terms. So we put some kind of voltage in here. Let's say we put 1 volt in. Well now, and we assume in most of these circuit analyses that everything starts at 0. It's a nice starting point. So right now, we've got 1 volt here, 0 volts here. So what's the op amp going to do on its output? So the non-inverting input is more positive. So this is 0 and this is +1. So it's going to output plus something. And if this were an open loop circuit, if we didn't have any feedback, this would go to the positive voltage rail, right? And it would go to saturation. But it's not. So this voltage starts increasing. We're looking at a very, very tiny time scale here. And starts feeding back into the inverting input of the op amp. So now the difference between these is getting smaller and smaller and smaller. The voltage here is rising towards 1 volt. That means that the op amp starts backing off on its output. And eventually, there's 1 volt here. So the difference between these is 0, what the op amp ideally wants. So that creates a voltage follower. The output here does whatever happens here. We talk about the op amp kind of hunting for the voltage. I kept saying that this is increasing and it's feeding back and it starts backing off on its output. That does happen, but it happens in an incredibly short amount of time. This is all happening on silicon, it's all transistors. So you're looking at, for all purposes, an instantaneous response of the voltage follower. And when you get into really high frequency stuff, maybe that's not quite so true. And that's where you have to look at those plots in the data sheet. So does negative feedback make sense any more so now? And why a voltage follower works like it does? Are there any questions about why a voltage follower works like it does? Because this is one of the building block circuits that you're going to use a lot. And we talked about, I'm not going to go back over the entire lecture last time, the hysteresis and positive feedback. If you have any problems with that, look at it, think about it in terms of this, or come talk to us. I'm happy to clear up anything. But The new stuff is we said last time that the name operational amplifier implies a lot more than just a simple amplifier, and that they use them in these analog computers to solve complex equations. And you can start seeing this. So let's look at F equals ma. So force is mass, change in velocity with time, right? Now let's look at an electronic circuit where we have the current through a capacitor equals the capacitance of the capacitor times the change in voltage with time. So we can start seeing a parallel between solving equations of physical systems and equations of these electronic circuits, right? So we can use the basic components like capacitors, resistors, and in this case operational amplifiers to solve equations like F equals ma if we wanted to. And that's the only way we had for a long time to do so. So we're going to show you summing, differentiating, integrating, and differencing with operational amplifiers at a pretty high level. Let's say that we have 3 voltages and we want to put them into some kind of a circuit, some kind of box, and on the output have all 3 added together, assuming that we've got enough voltage range to do that. You could come up with any kind of a number of scenarios for this. Say you had multiple transducers in a line and you wanted to add all of their outputs together to get total displacement on something or total force on something. Or you can imagine any number of situations where you want to add things together. Sure, now we have many channel digitizers where you could digitize everything and record it afterwards. That may not always be the case in your setup though. So we can use this building block circuit called the passive averager. This is one of those wonderful circuits that when you flip through Art of Electronics by Horowitz and Hill in like the very first 2 chapters that take up about that much of the book, you see a lot of things like this, pretty basic circuits that you may not have thought of on your own. So we've got 3 voltage sources, put them through 3 resistors, and if we say that all 3 of those resistors are an equal value, you can plug in the value there. You end up getting out the resistances cancel, and on this output terminal you get V1 plus V2 plus V3 divided by 3. So you've just now created the average of those 3 voltages with only resistors. But let's say we want to sum. Well, we're not quite to a sum yet. So do you see how we could take the passive averager circuit in an operational amplifier and create a summing circuit? Anybody have an idea? So what do we need to create a sum from that bottom equation? Right, so we just need to multiply by 3. We can use an operational amplifier with some negative feedback and a voltage divider, just like we talked about last time. So this can be a multiply by 3 circuit, and we have these 3 added together divided by 3 coming in. So on V out, you get the sum of those 3 inputs. Pretty simple circuit, but very useful. So let's say we put a 2K and a 1K resistor there. That'll give you the multiplier that you want. Let's say we want to look at the rate of change of a voltage coming in. We want to take the derivative of a signal. Let's say that you have a displacement transducer hooked up and you want to do some kind of control on velocity. So you want to take the derivative of that displacement signal in hardware. What components do you think we could use to do that based on what we've talked about in basic components from the basic electronic theory? So we can use capacitors as one of the building blocks for this and for the integrator, as it turns out. So capacitors, we know, pass AC signals through and they block DC. So if we make a little circuit like this, where you have Vn coming through a capacitor, you got your virtual ground here, and then a resistor that's going back to the output, the rate of change of the signal gets coupled into the circuit through the capacitor. The DC portion gets blocked out, and the combination of the capacitance and resistance sets the time constant for this circuit. And so you can plug that into the formula down there and figure out what V out you would get given a certain rate of change, dVdt, here. So let's say you had a signal another junk pin. So you had a signal, voltage, and time that looks like this. That has a fixed slope, and so you could plug that fixed slope into there, multiply by minus RC, and figure out what the output voltage would be. And then as you change the slope of that line, the output voltage would swing proportionally. So you see how that could work? Okay. So you could, in theory, create a system to, say, control on velocity of something with a displacement transducer with a circuit like this. So here are 3 input signals. So take a second, a couple minutes, and draw what the output of a differentiator would be for each of these 3 signals. You can forget 90% of what you know about electronics and just do Calc 1. Okay, so what's the derivative of a square wave look like? There's no rate of change in a square wave. Right. Yeah. Okay. It's better. So you go a very high rate of change here. If it was a perfect square wave, infinity, but no such thing exists, and that's why we hate square waves. So you've got a peak. It's going to decay. It's going to be sharper than that on the front. And then we go along for a while, and then we've got a negative peak. There's some RC decay, and then a peak up, and some RC decay. Okay, does everybody see why that one looks like that? All right. What about the triangular wave? The square wave, exactly. So you've got positive, because we've got a positive slope, and then negative, because we have a negative slope. And what about the sine curve? Cosine, yeah. So these are all things that, once again, you can use for things like peak detection, all kinds of trips on velocity, on load rate, or whatever. You can think of a lot of applications for this in the lab. And the integrator is basically the same thing, except the capacitor and the resistor have now swapped places, and we are now charging this capacitor through this resistor, and it's all in the feedback network. So, okay, there we go. What we end up doing is sort of creating this time averaged sum. So let's say that our input signal starts out at 0 and flops down to -1 volts. We're going to be starting at 0, and then we sum over that time. So we get this ramp curve until, in theory, we would sum way, way, way out. But we're going to hit a voltage rail eventually. So it becomes flat when we hit the saturation voltage. If you change the RC value, you can change the time constant over which you're integrating, so you can get a faster or a slower response from the circuit, more or less memory effectively. So, good so far? Okay. One of the nice signals in electronics is a ramp generator. We actually use them in the lab for several things. You can create these nice sawtooth looking waves. One way to do that is to use an integrator and feed it a square wave, right? So we're positive here, or we're at 0 here, so we're going to be going down. We go to -1 volt, we go up, and we have these nice ramps or sawtooth patterns. Right? The last circuit that we want to talk about is one that we actually use a lot, but not in this form, and that's taking a difference. So if you look at your circuits that we've done so far, you've probably drawn them in your notes, or maybe you have the slides. They all have ground referenced inputs, right? We have one input coming in. We have one VN. One VN there. The voltage follower has one VN. What if you have something like your Wheatstone bridge that you just created, and it does not have a ground referenced output? You take the difference of the two terminals coming out. You've got say +5. You're measuring the difference between these. That tells you the strain. Well, it gets a little bit more complicated, and to do that with a regular operational amplifier, you have to create these two divider networks, one in the feedback loop and one to divide the input that it's comparing to. That looks great on paper, and you say it's just 4 resistors, and we had 2 resistors before. This isn't hard to implement. The catch is, if these resistors are not perfectly matched, you will get an input offset error. And if you have significant amplification, you just blew your entire voltage range on input offset error. Even 1% resistors, 1% tolerance aren't really good enough for this. You need 0.1 at worst, 0.01 is better. And those resistors can get expensive. So it's not really an ideal setup. You can do a little bit better if you set up 2 voltage followers. So you've got negative feedback on both of these. And then those dividers, because now at least you've got a very low source impedance for those voltage dividers and a very high input impedance for your signal, which you may not have had before, but you still have to have those precision trimmed resistors that can be expensive. So there's this thing, the Instrumentation Amplifier, that is all one chip. So it's a monolithic chip or monolithic package. This is a really rough diagram of what's inside an instrumentation amplifier. So all of this is in one chip. You have 3 operational amplifiers, and this resistor, R gain, is 2 of the pins. It's exposed to you. So you insert R gain in the circuit, but everything else is on one piece of silicon. And when they manufacture these, they actually have a laser that they go in on the die and laser trim these resistors to be the exact same resistance. If you look on the die, you can actually see the little cut where the laser goes through, and they measure it as they're cut. So this creates a really, really nice low offset, high impedance amplifier for you. Offsets of like nanovolts on the input, or maybe even a little bit less. And you don't have to worry about getting all these components and doing layout on a circuit board. you just have the part and one resistor. So there's a bunch of them out there. This is a board that I designed a while back, and there are 2 instrumentation amplifiers on it and some voltage regulators and other stuff. But really, this is all that's necessary to make this work. The idea is you put in a differential signal, say your strain gauges or DC-DT, and you select what amplification you want with one resistor. So here there are 3 resistors, and you select which one you want by how you solder this together. And you have a really nice low noise differential amplifier that has a single-ended output. One of the amplifiers that's my favorite, there's a lot out there. Analog Devices has a series of them, the AD600 series, so the AD620, 630, 680. Texas Instruments has their INA series for instrumentation amp. The INA 105 was a really, really common part, and they still make it. They've upgraded it now with the INA 128 and 129. And I've got some INA 128s that you're going to use on Thursday. But yeah, so look at the offset voltage is 50 microvolts maximum, 0.5 microvolts per degree drift maximum, 120 dB common mode noise rejection. So remember, 40 dB would be like a factor of 100, so we're way, way above that. And a lot of instrumentation amplifiers have these built-in things like overvoltage protection. A lot of the cheap, just kind of jelly bean op amps that you might get, the OP177 or the LM741. If you go much above the supply voltage, so say you're supplying it with 5 volts and you accidentally on the input put in 12 volts, it will release the magic smoke, and that will be the end of that chip. These are protected, so plus minus 40 volts on the inputs before you start having problems with these. And you can kind of take a belt and suspenders approach and use diodes like this to really clamp the input. Here, if you go above the supply voltage, these diodes will turn on and clamp the input to the supply voltage, and they can do that up to a couple amps before they blow up. So if it's really important that you not blow out the instrumentation amp in your circuit, say it does something like control a hydraulic press and you don't want your hand to get crushed off, you should do things like make sure you have good overvoltage protection and out of range protection. Really, like the INA 105, it had a pretty wide supply voltage range. These can run from plus or minus 2.25 to plus or minus 18. Things are really starting to push down lower and lower voltage these days. And so 700 microamp current. So these are really nice. And you'll notice under the applications, a bridge amplifier is the first one. This is purpose designed for doing things like Wheatstone bridges, scales, there's a thermocouple, RTDs, all these things that we've talked about so far. And this is from the datasheet of the simplified schematic. So it looks pretty much like what we talked about already. There's a little bit of a feedback loop here. Then you've got the dividers going into the final difference amplifier. These overvoltage protection circuits up front, which are really just a couple of probably Schottky diodes in there. And then they provide formulas for you to plug in so you don't have to do all the circuit analysis yourself. You can set what gain you'd like. They also have tables in the data sheet that say if you want a gain of 500, you can use this standard 1% resistor that you can buy and it'll get you a gain of 498 or something close. The closer you want to get to your absolute gain value, the more expensive the resistors get. They also mention in the data sheet something we talked about last time, which is don't forget about providing a path for your bias currents. So if you've got something like a thermocouple or a microphone that's going to be generating some current, it needs to have somewhere to go. And in theory, no current flows in here. So use a couple high-value, well-matched resistors and give that bias current a ground path. Otherwise, you will get very erratic behavior. You're not going to have to worry about that for your circuit this week, though. So this is an image, again, from the datasheet of exactly what I've drawn here and what you've built already. So on Thursday, I'm not going to give you a schematic or a little picture diagram because that's it. It's in the datasheet. It's all ready to go. and it has the pinout for the chip in the datasheet. One thing that you can do, and some of you, excuse me, might need to do this, some might not. Let me put the screen up and just draw it on there. Is change this reference terminal. So that terminal changes the 0 point for your amplifier, where 0 difference is. You should not have a large offset out of your amplifier, out of your bridge. If you hook your bridge circuit up to a power supply, you should have an offset of a few millivolts, maybe 10 millivolts. If you've got more than that, there is something wrong, and you should find us and look at it. Volts are right out, because that's a huge common mode value that we're not going to be able to get rid of. But if you do need to do a little bit of offsetting, I did this with my coffee cup, because if you take, say I have 4 millivolts, but then I multiply the signal with a gain of 500 times, all of a sudden I have a pretty large voltage on the output. And I can offset that if I want 0 load to be 0 volts. And one way you could do this would be, instead of tie that to ground, you put a resistor in there. Let's say we give it plus 5 volts. Let's do it like this, actually. Make it a little bit clearer. You can't see it. Use a potentiometer, create a voltage divider with it, and put that voltage into the reference terminal. There we go. Plus 5, and do that. You should not do this in a laboratory application. It's fine to use the reference terminal to do offsetting, but you need to buffer this. You need to put a voltage follower right here in between that, because the reference terminal is expecting a low impedance input, and this is probably not going to be low impedance. You're going to have something like a 5K there. But it'll work fine for doing the lab. And you don't have another operational amplifier to use. Okay, so any questions about op amps, doing math with op amps, instrumentation amps? No? Okay. So there are 2 things. Let me give one out and then the next. These are real circuits that we have in the lab right now. These are part of the biax control system. If you're not familiar with the biax, that's fine. If you are, it might help a little bit. And let me give you the other one. So the one I just passed out is the fail-safe circuit, which if you go too far in displacement or too high in load, locks the hydraulic piston, so bad things don't happen. The one I'm getting ready to hand out right now is the Lvdt signal conditioning circuit that takes the input from the Lvdt or DCDT and passes it on to the servo amplifier. So you can pick which one of these you want to look at. They're both roughly the same complexity. And the nice thing is we have talked about enough in the last 3 weeks or so that you can actually fully analyze what this does and how it works. You don't have to do all the math necessarily, but get together groups of 2 or 3 people and try to figure out how each of these circuits works. And then in about 10 or 15 minutes, we'll get back together and discuss it for a little bit. Okay? So let's talk about these for a few minutes. You did the failsafe. Okay, did anybody do the Lvdt signal conditioning one? Did they look at that in any detail? No? Okay, well, let's look at that one then. You all picked the harder one to do. Okay. So in this case, we've got a DCDT, Lvdt, labeled on here, differential input coming in, going to this INA 105. So that's serving as, and I made it easy because I wrote it on here years ago and didn't have a clean copy to photocopy for you. That's a buffer. So that's just a one-to-one buffer. So we don't load down that instrument, and we have a low impedance output. And that's going into another INA 105 as a single-ended input to the non-inverting terminal. And then up here, we have a triple pole double throw switch with some resistors connected between these 5.62Ks and this 5K potentiometer in the center. This is kind of a funny setup, but what we're doing is as we move the switch, we're changing the voltages with these dividers that are on each side of the potentiometer. So the potentiometer has, this is a 10-turn potentiometer as it turns out in real life. You have a very fine control over that range of voltages. Then you can flip the switch and have a very fine control over the next range of voltages, all the way up to the plus rail and the minus rail. So it's just a switched voltage divider and a potentiometer. So lots of voltage divider math. That goes in with the buffered signal into this amplifier, which once again is set to be a unity gain. So that just offsets the signal. We have a single-ended input here, single-ended input here. That's how you zero the transducers on the biax if you've ever used it. But we're just offsetting the signal. Then that offset signal now goes into this OP177. And what circuit does the OP177 make? What's it hooked up as? So it's an amplifier. It's a voltage follower with an amplifier on it. We've got these resistors in the feedback loop, basically, and we've got a capacitor that makes it, strictly speaking, a low-pass filter. The capacitor actually isn't in place in the real biax, we found out. Last time I looked, anyway.
It was in there originally, yeah, it's causing trouble, and been in and out many times. It's pretty.
And so you can see I actually done some math over on the other side. That gain switch 2A is a gain switch, and we have gains of about 2 and about 12 in real life. Then, on the output of the OP177, there's an IA105, again set up as a buffer, down through this little divider. And this DPM, I didn't really expect people to get too much into that. This is a panel meter. If you look on the biax, it's the digital LCD display of the voltage. All this does is buffer and do a little bit of division to get everything in the right range for the panel meter. Okay, so does that make sense how we process the Lvdt signal or DC-DC signal with a circuit like this? It looks pretty simple, but it's not necessarily once you start getting in the fine details. Down here in this corner, we just have decoupling capacitors on the power rails, which help filter the voltage to make it a nice clean signal. Okay, so now onto the one that everybody did. That's actually a little bit trickier. So in the top left corner, you have an OP177, and you've got this front panel set point coming into the non-inverting input, and then you have feedback on the inverting input. Okay, so what are we doing there? So that's a unity gain inverting amplifier. So it's going to take whatever voltage is here, invert it, and spit it out there. It's like a voltage follower, but with a -1 multiplier. Okay, then we have a load cell input. So the output of that and this load cell input are going into the next 741. So what's it doing? So we've got the load cell signal and this set point coming in. So it compares them, right? And there's a little bit of hysteresis in there. We've got a little bit of positive feedback going on to make sure that once you trip on the load going too high, the load going higher than the set point, you stay. And then there's some LEDs to show you that you've tripped. That's what would be up here. Now, did anybody figure out what's going on with all these diodes coming out of all these? We looked at an example like this in class in a simplified form. Didn't have all, take away all the op amps and just think about signals and a bunch of diodes connected like that. No, not exactly.